We talked about Bronsted-Lowry acids and bases in class, but I thought I would just review the ideas just a little bit more. So, in the Bronsted-Lowry system, an acid donates a proton, and you remember that when we say a proton, we are in fact talking about a hydrogen ion. So a proton and hydrogen ion mean the same thing. And a base is the thing that accepts the proton. So if we compare for this reaction, if we compare the left side to the right side, what we see is that the hydrogen is moving over here, and it's leaving its electron behind with the bromine. So over here, the H3O plus has gained a positive charge. This slide is going to make more sense later on after we've talked about electrons, but essentially, there's no use to it. Okay, at this point we can take a look at what happens when strong acids and strong bases react. So this is a list of the 6 common strong acids and the 6 common strong bases, and even within the realm of the 6, there are some that are more common than others. So, for example, in class we will run across this one, obviously, and nitric acid and sulfuric acid, and I would be surprised if we used any hydrobromic, hydriodic, or perchloric acid. In terms of the bases, it's conceivable we would at some point see all of these. However, far and away the 2 that are most common are sodium hydroxide and potassium hydroxide. Now, we can talk about what happens when we have a reaction between, let's say, hydrochloric acid and sodium hydroxide. Again, we're just going to assume a double replacement situation, which is in fact what happens, and we can write the products like so. If we take everything that is strong and break it into ions, and everything that is soluble and break it into ions, we're going to have a situation that looks like this. Salt NaCl is, of course, soluble, and water is essentially unionized. So if we were to put the conductivity device into a sample of water, we would get almost no measurable ions. It turns out with very sensitive equipment we can measure a few ions, but for our purposes right now that's really not part of what we need to talk about. Okay, so what do we have that stays the same on both sides of the equation? Well, the chloride is the same on both sides, so that is a spectator ion. And the sodium ion is the same on both sides, so that's a spectator ion. So we are left with the following. So what we have is H plus OH minus yields H2O. So for every combination that you see above, that is going to be the net ionic equation with one exception. When you react sulfuric acid with barium hydroxide, you will get the salt will be barium sulfate, and barium sulfate, if you check the solubility rules, is insoluble. So at some point we'll talk about that a little bit more in class. Well, what happens if we have something that is not a strong acid and we have that reacting with a strong base? How is that going to differ from what we've already looked at? So I guess a question we might ask in the very beginning is, how do we know we have a weak acid? So if it's not on this list, if it's not one of these 6, and it starts with hydrogen, you are going to assume it's a weak acid. So, for example, hydrofluoric acid is not on the list, And so we can take a look at the reaction of hydrofluoric acid and, let's say, potassium hydroxide. Okay, when these two react, we go through the same process that we did before. So we're going to have KF and H2O. We break everything into ions that is either strong or soluble. So hydrofluoric acid is weak, so we do not separate it into ions. Potassium hydroxide is strong, so we do separate it into ions. Potassium fluoride, if we check the solubility rules, is a soluble salt, so that's going to be ions, and as usual, water is written together. So we can go through the process and we can cancel out everything that stays exactly the same. So in this case, we can only cancel out the potassium ion. So careful, you might be tempted somehow to want to get rid of that fluoride ion, but over here it's connected with the HF, so you can't cancel it out in that situation. So we end up with the following. So we have HF plus OH minus, and that yields the anion, the fluoride ion, and we also get water. And so this is going to be what you'll see when you have weak acids. So in other words, acids that are not on this list, and they are reacting with something that's on this list. So that covers, quite a few reactions. I mean, just for the record, there are hundreds, if not thousands, of weak acids. So that's just a lot of reactions that you get just from this information. And on a test, I will give you this exact list along with the solubility rules. So you don't have to memorize this. It's probably fairly useful to be aware of what are the common strong acids and strong bases, I mean the super common ones, but you don't have to memorize it. Alright, so that leaves us one more case to look at, which is a weak base and a strong acid. So we can do that next. Okay, so let's clear this stuff out of the way. And take a look, at what happens when we have a weak base. So at the moment, let's just consider really the only weak base we're going to talk about for a while. So let's say we have ammonia, and we will look at that reaction with hydrochloric acid. So hydrochloric acid is the acid, ammonia is the base, so the hydrogen goes there. That means on this side we're going to have the ammonium ion, and we're going to have the chloride ion. And I could have said at the beginning that over here we would also have that for hydrochloric acid. Okay, so what can we take out of this equation? So the chloride ion stays constant on both sides. So really this one just looks like this. It's just ammonia reacting with the hydrogen ion, and we get over here the ammonium ion. So right now this is going to be enough for you to know in terms of the weak base strong acid. And we don't really consider too much at this point in chemistry a weak acid reacting with a weak base. So this kind of covers the main examples.